All right, page 614, you had 4 questions. Number 5, what is the period of a pendulum with a length of 0.45 meters? Oops, okay, why is it doing that? So you're going to use the equation, I don't know why it's just being a pain. T is equal to 2 pi root L over G, the period of a simple pendulum. Okay, so we're just looking for T, so 2 pi root, the L they told us was 0.45 meters, and the G 9.81 meters per second squared. Do the math and you should get a period of 1.346 seconds. Number 5 is done. Number 6, what must be the length of a pendulum to give it a period of 4 seconds? Ooh, so this time you have to rearrange. You're looking for L, but I trust you can handle it. So it'll be T over 2 pi is equal to root L over G, square both sides. And so you get T squared over 4 pi squared is equal to L over G, multiply both sides by G. So L is equal to GT squared over 4 pi squared. So is equal to 9.81 meters per second squared. Said the period you wanted was 4 seconds squared over 4 pi squared. The most common mistake, not to square the things even after you write them down. You end up getting an L of 3.976 meters. 3.976, yeah. Number 7. Every swing of the pendulum in a clock causes the second hand to move an angle representing exactly 1/2 of a second. So every swing, so think about the pendulum on like a grandfather clock. So a swing is all the way over, is a 1/2 a second, and all the way back is another 1/2 a second. The period is over and back, so the period is 1 second. Okay? What must be the length of the pendulum? So again, T is equal to 2 pi root L over G, square both sides, rearrange it so it becomes T squared over 4 pi squared equals L over G. So L is going to equal GT squared over 4 pi squared. So 9.81 meters per second squared times 1 second squared over 4 pi squared. The length of the pendulum of the clock should be 0.248 meters. So the trick here in this one was to realize one swing is half the period. So a 1/2 a second over, a 1/2 a second back. Number 8 says, if the pendulum has a period, so T, of 0.36 seconds on Earth, what will its period be on the moon? Okay, so the first step is to find the length of the pendulum, because the length isn't going to change whether you're on Earth or on the moon. Okay, so 2 pi root L over G, and again rearranging like we did up there, so T squared over 4 pi squared is equal to L over G. So L is going to equal GT squared over 4 pi squared. So L is going to equal, on the Earth, it's 9.81 meters per second squared. The period is 0.36 of a second squared over 4 pi squared. And you will get an L of 0.0322 meters. Okay, so now you're going to take this pendulum with its L, and you're going to go to the moon. So the period for the moon should be 2 pi root L over G. So 2 pi root 0.0322 meters. And the G on the moon, if you don't remember it, it's on page 133, 134 in your textbook. And according to your textbook, it's 1.64 meters per second squared. I think when I did it, I used one that I found instead of your textbook one, so I just need to check the answer here. So I guess I really need to go back now and do 0.36 squared times 9.81 divided by 4 divided by pi squared, because otherwise my answer will be rounded. And now I divide that by 1.64, take the square root, multiply by 2, multiply by pi, and I get a period of 0.88047. 0.88047 seconds. The 4 questions in the textbook were done, and hopefully we're not that bad. I also asked you to do questions 7 and 8 on the front side of your sheet, so these two. So let's take a look at 7. We probably don't have time in this video to get them both done, but I should be able to get 7 done maybe. 7 is a 3 kilogram block sitting on a frictionless horizontal surface. Okay, and I'm going to assume it's attached to a spring. So this is 3 kilograms. The block makes one complete oscillation every 2 seconds, so it means the period is 2 seconds. If its maximum velocity during the oscillation, so this is where x equals 0, and this is your v max. So maximum velocity is 5 meters per second. What is the amplitude? So how far out? What is x equal to out here? Out here, v is equal to 0. Okay, so the first step is you have to find k. And to find k, you're going to use t is equal to, not 2 pi root L over G anymore. It's going to be 2 pi root M over K. Divide both sides by the 2 pi, square both sides, bring the K up, bring the 4 pi up, so you'll get K is equal to 4 pi squared M over T squared. So K is equal to 4 pi squared, M was 3 kilograms, and T squared was 2 seconds squared. 4 cancels, so 12, 29.6088 newtons per meter. So now we go to conservation of energy. 1/2 mv initial squared plus mg h initial plus 1/2 kx initial squared is equal to 1/2 mv final squared plus mg h final plus 1/2 kx final squared plus E lost. No E lost. If we call this our initial and this our final, initially then no speed, but no height, but it has an x. Finally has a speed, no height, no x. So we have 1/2 kx initial squared is equal to 1/2 mv final squared. The halves cancel, and we're looking for x. So x initial squared equals mv final squared over k. So 3 kilograms times 5 meters per second squared over k was 29.6088 newtons per meter. And remember, what you get here is going to be x squared. So x squared is 2.533 meters squared. Take the square root, and x is equal to 1.59155 meters. Number 7 is done. Number 8 says, a block sits on a frictionless horizontal surface. Imagine. Okay, so here it is. X is equal to 0. Sure, it's going to get stretched out here to some point where V is equal to 0. Whose spring constant, so they're telling us the K. Spring constant is 20 or 20,000. I think it's 20. I was trying to see if that was a decimal or a comma. If its maximum velocity, so right here, V is equal to 3.5 meters per second, and the amplitude of the oscillation right here is 2.8 meters, what is the mass of the block? Okay, so again, kinetic energy, so 1/2 mv initial squared, mg h initial, 1/2, going to run out of time, kx initial squared is equal to 1/2 mv final squared, mg h final, 1/2 k. See you in the next video.